All right, welcome to the Need for Speed seminar series. I'm Janak Patel, no relation to the organizer for this seminar series, Professor Sanjay Patel, though I get sometimes credit. Okay, should we start? All right, welcome to the Need for Speed seminar series. I'm Janak Patel, no relation to the organizer for this seminar series, Professor Sanjay Patel, though I get sometimes credit for what he does, great stuff, you know. But now, today we have Professor Ahuja and some tidbits of something I want to tell you. He's the longest serving faculty member of the computer engineering faculty. I don't think there's anybody has served longer than him. He's so continuous for many years here, and has many achievements that you probably saw. But other things he's known for is, because I remember I was sitting in this audience when he got his chair professorship and giving an acceptance speech. He read a poem, and he's known for ghazals. This is like a poem in India. Is well known for that also. If you can ask, maybe he might even sometimes do these ghazals. So besides technical things, he does a lot of other things. He has established, responsible for an institute of technology called IIIT in Hyderabad, India. Single-handedly is made into a equivalent of an IIT there with already many students and faculty. So many talents, but today he's going to talk about his video. So, Professor Ahuja.
Thank you. Do you want me to tell stories about you? All right, so need for speed. So what I thought I will do is cut down on the details of the vision side of things, details which probably won't matter from the viewpoint of speed, but still give enough details so that you get a flavor. Those of you who are not in vision will get a flavor for what is involved from architecture and from design point of view. So before I do that, let me give credit to people whose work I am reporting today. So those are the people who are whose work is included in what I'm going to talk about today. All right, and most of the computations that that would be involved in everything that I talk about can be categorized into those two. First of all, images and video, but from the viewpoint of computation, either those computations are done on the image or on the video. So let's look at the image part. So the computations mostly are either on pixels uniformly in the SIMD type. In my days it was SIMD. What is it called now? Still the same?
Same thing.
So it's SIMD type, which is 2D array. So it's pixel. Oh, great. Yeah. So computation on a pixel or a small neighborhood of a pixel, which is I would say 99% of the vision computations are of that category. Then a computation on not local neighborhood but the entire image. Then you get into this primitive set of primitives which are not pixels, which are collections of pixels, usually local collections of pixels. They correspond to regions which are precursors to objects. So those can be organized in different ways, either as trees or graphs, and we'll see why they give rise to trees or graphs. But the point is here, from the viewpoint of architecture and computation, that these are not pixels, these are collections of pixels, and therefore not regularly placed. So they are arrangements of objects, like people's heads in this audience. They are not along a grid, and if you want to do something about if you want to compute something that reflects people's presence, then it will have to go and access each head, which means you have placement of objects which are not predetermined, which is not along a regular grid. It's not in a predictable place. So those are then organized in trees and graphs. And then in video, you do the same thing, except that now either you take sequence of these things. So you have video means sequence of frames. So you have the same kinds of computations happening independently on each frame, or you can have a volume, space-time volume. Think of video as x, y, and t, and in that x, y, t, you can think of the pixels as samples of three-dimensional space, x, y, t space, and look at all of these in that light. So these are not independent frame things. So all of these then get reflected here as a higher dimensional version of what we did here, and then that can go on into, if you have a 3D object with a radar or with a 3D image with radar or something else, then you have a 3D image kind of, and with time you get 4 dimensions. So most of the computations that we'll either explicitly mention or not mention, but they are implicit, are in one of those categories. So what I've done is I've taken one example, which is one of our projects, but it's a good example because it brings out lots of different kinds of computations in one running theme, and we'll stop and see what computations characterize each of these different steps. So the running theme is that suppose you are given a set of images. The question that we need to answer is, are there any characteristic themes to it, to that set of images? And theme in this case is rather mundane definition, very simplistic definition, which it says that, do you see something that repeats a lot? That's all. That's the theme. So if there is an object that repeats a lot in an image or in a set of images, then that object's name is the theme. So here, for example, the theme is, one theme is, and it doesn't have to be just one, horses could be repeating, and cows could be repeating, and people could be repeating. So the theme is whatever it is that is repeating, one or more such objects. All right, so computation-wise, the need for speed issue here is that for whatever reason, we decide that in order to address that question, what we do is we convert the image into a tree. So in other words, you take the image and you represent it as a hierarchical jigsaw puzzle. So something says that somehow you decide that this image is to be tessellated into this little thing which corresponds to that part, and then that. So these are all pieces. This one comes from there, and then this piece, this layer itself, is then further decomposed into smaller jigsaw puzzles which are contained inside the parent piece. So the pieces are organized hierarchically. So in the end, you really have a tessellation, and the tessellation of tessellation, and tessellation of tessellation, like from here to there. So these are just some snapshots. So this is an algorithmic step that we have chosen for some reasons, for good reasons. Now the question is, what are the computational implications of this? So for one thing, the creation of the creation of the tree from the image involves visiting pixels, each pair of pixels in the worst case. For each, you go to each pixel and you relate it to every other pixel in the image. So you really have to, your architecture has to support pairwise high-speed access and computation. So when you have 2 pixels in your 2 hands, you can do some computation on them, dump the value somewhere, and then do that again and again and again. So if you do that, then you can create this tree. So anything that would be hospitable to pairwise access and computation across the image, and do it multiple times. So it will be iterative several times. That will create the tree, and now of course you have to organize the tree in the obvious way, so that later on you have access to it. So as a result, what you get is a collection of such trees for different images. And you remember our goal was to discover the theme across images. So now that problem becomes that of discovering a theme across the trees, because images have been replaced by trees concisely. So the question is, are there themes? And themes we define to be repetitions. So are there repetitions across these images, which means are there repetitions across these trees, which means are there subtrees that recur? Okay. Subtrees recurring means their structure recurring, and what I didn't say earlier was that each of the node in the tree is now has a vector of properties which relate to whatever it is that is captured by that node. So each node in the tree has associated image segment which corresponds to something meaningful. Of course, nothing is known about meaning here. So you just extract some properties and hang that list of properties from this node. So what we end up getting is this tree of nodes. Each of those nodes has a vector along with it, which are the properties of that geometric and photometric entity. So that now is a horrendous computationally process. What you have to do is you have to take, suppose I've got a set of 10 images, and I want to find out, are they recurring objects, right? That means that we are interested in knowing whether any object, which means any node, is recurring frequently across the image set. How do you know whether it's recurring? You have to compare them. Are these two the same? Are these two the same? Now that suddenly means if there are so many n nodes here and n nodes here, you have n squared observations and computations to make. But we are not dealing with 2 images, we are dealing with 10 images. So you're talking about n times n times n times n to the 10. And that is already too much, because these trees are not very shallow. It depends upon the image, of course, but in this room, for example, the tree will not be shallow, it will be 5 levels. And of course, it's up to you. You can be very meticulous about the content, and you can say, I want to really get the last bit, then you will go more levels. But so we are dealing with a real challenge. In most of our implementations, of course, it's sequential, and so we don't even bother to do the 10. We just say, okay, give me the result of these 2, and then take the result of those 2 and compare that with the third and fourth. So it's already compromising a lot. But ideally, you want to put those 10 things into a bag, and out comes that nice set of matches across the entire set. So subtree isomorphism here is what we are after, and essentially it boils down to finding the max clique in these set of trees. But when we are done, what we end up with is from different trees we end up getting matches of the different nodes. So there are many mustaches, many noses, many eyes, many faces across the images for repeating objects. They will show up as matches and sit in that set of matches. So now what we have done here is condensed as a result of matching. As a result of matching, we have condensed that whole process into this nice result where each rectangle contains the set of corresponding nodes obtained from across trees as a result of matching. And our goal now is to take each of this set, which are different because they came from different people's faces, and yet they are either mustaches or noses. So while mustaches are not all the same, they are still more similar to each other than to nose. So what we do is we come up with a canonical representation of each of them, with a canonical nose, canonical mustache, and so on, and those are now represented in a condensed tree which represents the object that was recurring. So this tree is a representation of that class of objects that is recurring. So in case of faces, this would be the entire elliptical region corresponding to face. Then maybe there will be eyes and nose and so on, and then there will be eyelids and the pupil and so on. So recursively smaller contained regions. But the thing is that none of these nodes is pure, in the sense that every single node represents many occurrences of the same thing, and they are all different. So you have to come up with a representative description, and each of these now is a probability distribution. Each node has a vector of not of properties, but a vector of probability density functions, where each entry corresponds to some aspect of the nose or the eyelid or the pupil or whatever. It's just a sort of a canonical pupil or canonical nose or canonical this and canonical that. So,
can I ask you a question?
Yeah.
You can repeat it, right? The previous slide. Can you go to the previous slide? What is the exact numeric computation that is occurring to say what is matched, like in the eyes case? So, is it a statistical? It is floating point? Is it? This is from a need for speed perspective. I'm wondering. What is that computational complexity of matching two things?
So the question is, what is the computational complexity of matching across trees so that we get this resulting tree? So what you do is you take, so the dumbest way is this: you put your hand on one tree, go down, traverse it, and as you are putting your hand on one node, you slide down the entire tree with the other hand and compare the two. Match, no match, match, no match.
So what is the matching thing itself? Is it statistical or is it
statistical? Statistical. It's based upon the attribute. So for example, you match the, I didn't bring a, so the properties that you base the match on are properties that you think are responsible for visual perception of similarity of objects at very low level. So such as shape properties, color properties, topological properties. So this is a long, so originally in that first tree that we created, it's a segmentation tree, the recursive tessellation, there we had a long list of properties associated with each node, which means properties of the shape and photometric properties and the structure. So in the end, what we get is a description of the whole object. This is now one object repeating, and it's given by the whole object, that its parts, and so on, and how many subparts there are, how many, what the color distribution is, how they co-occur. All of these things are now represented concisely as statistical summary of what you saw. So this is a representative of this diversity here. Okay. So as a result, what we get is from that horse image, what we get now is that the repeating object, which is horse, is now extracted out, and it is extracted out because it is represented, it is recognized, and in terms of the representation which we extract here, which is that the horse looks like this. It's made up of those parts. So then let's just consider this. This guy found two different objects, so we'll ignore this. But there are two, then those are made up of parts which are smaller and smaller and contained. So this essentially now becomes our understanding of the object, one object that repeated, and this is the category model, the model. Now you can use this model to look at any new image and ask the question, do I see or do I not see that object? How you do that is that you obtain that recursive tessellation segmentation tree of this. So now you have an unknown image, you have a known tree. You take that little subtree that you extracted here, this one, this which is represented pictorially this way, you take this and you rub it against the tree of this image and see if there is a match of the same kind that we used to obtain the model in the first place. And if it fires up, you say, yes, I've discovered it. But once it fires up, you know where exactly the object is, where its legs are, where its tail is, because all is captured in the model. So not only you know if the object is there or not, you know exactly which parts it occupies, one or more occurrences, and which part is tail, which part corresponds to the bottom layer, which parts correspond to the middle layer, which parts correspond to the top layer, and so on. So you get a lot of information from this. So let's see, computation wise, here what we have done is basically the same thing, matching against the. Now the matching, by the way, is not plus minus thing. You have to ask the question, does this guy in the tree is a good instance of the probability density function that was represented by that node in the model? So it's not, is the difference large? The question is whether the properties of this set of this subtree corresponding to this region, and of course we don't know a priori. So there is a tree here, and you are sliding your model tree with against the subtrees of this, and each time you ask, is my observed subtree a good random instance of the PDF that governs the model underlying, which is associated with the learned canonical tree. And if it does match, meaning if it represents a good instance of that, then you say it's a detection, otherwise not. Now let's go to a little bit. Yeah.
Yeah, that's a silly question. So how precise this can be? For example, can you tell difference between a horse and a donkey? Yeah.
Right. So that, I think that's a very good question. The question is whether it can tell the difference between a horse and donkey. So there is that standard issue of stability and sensitivity, discrimination versus recognition. Like for example, in speech, you want to be able to recognize the letter, the word donkey, the word spoken. But at the same time, you also want to recognize whether I spoke it or somebody else spoke it. So there is this perennial tug of war between you want to generalize or you want to specialize, because both are important. So here again the same thing, you want to recognize horses, but at the same time you don't want to confuse them with donkeys. So then you have to come up with distinctive features, and that's coming up. So in real world, there are not one or two or three categories, but there are many categories. So in this case, what we did, we ran our system on this set. Now, can anybody guess what those who don't know it already, what categories would be found here? Just a quick guess. I can guarantee you will be wrong. Huh?
Grass.
Grass?
Yeah, all species of grass.
All right.
Horses, of course.
Horses. You are more wrong than him. Huh?
White animals.
No.
Sky. Black and white pictures.
No. Let me show you what it got. So this thing is very dumb. It has absolutely no intelligence at all. All it says is, do I find structural pieces that are similar, pieces that are similar in structure in terms of topology, pieces that are similar in color, pieces that are similar in shape. That's all. So it says, and it doesn't know what. So it has it in its own mind. The system has discovered a category. It says, I see these things occur a lot, so it must be meaningful. So I give a word to it. I give a name to it. And there's those longish. The red doesn't mean anything here. The longish, grayish things are meaningful because they occur a lot. And then it found this thing also. More. Now there is a lesson here. These things are even though we don't pay attention, but these are very meaningful, because after all, they are limbs on which, at least in the photometric, in geometric and topological sense also they are meaningful. Of course, semantically they are meaningful because the thing stands on it. But so these things, so what this says is that our category that we are talking about is a category that is made up of many subcategories which we don't even pay attention to. They exist, but to us they don't mean much, because if we started to keep track of all these guys, our space will fill up. So this one is, we only keep track of the sky and the grass and the horse, not the little things that make them up. So the idea here is that the categories are formed by configurations of other categories which are smaller and recursively so. And therefore, the definition of category is its layout of subcategories. Recursive definition. At some level of recursion, we start to say it's meaningful. So the lesson here from the viewpoint of representation and from the viewpoint of computation is very profound. And even from the knowledge, human knowledge representation point of view, it's very profound. And that says that we know many things in the world. Our vocabulary is large, we think. But the amount of representation size, the size of representation that we need is not proportional to the vocabulary size. We have lots of these guys, but the horse and the cow both share legs, and we only have to have one leg representation. Human and the horse share legs. The difference comes in the count at one level. So now if you can separate the count from the representation of the leg, you have immense savings, because what happens is you have upward divergence. You have many guys being represented by fewer and fewer entities. Eventually everything in the world is made up of charmed quarks, if you go down in physics. So that's it. There is this unity in diversity. Diversity appears to mortals as meaningful, but actually it's manifestation of fewer and fewer things as you go down. So it's the same thing at very, in a small window, macro level. So here we have certain shapes, certain colors conspiring to make up, to look like different things. However, okay, so in terms of computation now, we are gaining in the sense that our world representation is not a collection of object representations. Its object representation, if we were to use, would give a linear size, linearly increasing size of the world representation. But that's not true. Our world representation is not linear, it's sublinear in the number of categories. And that's a great property, because that's how perhaps we can afford to fit it in our heads. So taxonomy now can be generated by this tree matching. You have many images, you can do this matching and get these classes, and you cluster them into, so different donkeys become one donkey class, donkeys and mules then become one whatever that class, and then at some point they join horses, because they have to be distinguished from humans or airplanes or something. So the difference is increasing, and you are grouping them by clustering. So taxonomy is, if you feed lots of images to the system, it will keep generating this tree where more and more differences will characterize higher level objects, and smaller and smaller differences will characterize lower level things. So philosophically, this whole approach can be, we don't have time for that, but it has lots of correspondence correspondences to many other descriptions that are associated with other phenomena and objects and so on. So at the end, you have now learned, the system has learned, not a single tree, but a taxonomy that represents the world. The world is captured in the images that it saw. So if you give it 10,000 images, it would represent it by a sublinear interleaved tree in which the size of the representation is not as large as is not proportional to the number of categories. And then you can use that whole taxonomy, that upward diverging tree, to discover everything, the horses and the donkeys and the mules, because everything is captured in this taxonomy. The higher up in the taxonomy it is, the more supposedly different it is. Okay, so clustering. So this represents progressively increasing size of the clusters. You know, first you didn't include the mule, then you include the mule, and so on. And then, so let me just take a digression here, because clustering is such a big problem. I'll come back to this to get to other issues. But clustering is a problem that many of us in different disciplines face. And these days, of course, with all the net accessible data, we have many reasons to cluster. We have reasons to cluster because we want to get similar apparel on the net, or we want to cluster similar faces, or similar looking buildings or flowers or whatever. And it's a generic problem. Since the attributes for each node in our case had the shape properties, color properties, and other geometric properties, the dimensionality in which you do clustering ends up being large typically, and even more so in people who do, for example, computer modeling, performance modeling, and so on. The dimensionality of the space in which you do clustering is very large. In our case, it depends. It's typically in visual case, you know, you probably have under 10 dimensions, but you can also construct problems where the dimensionality is very large. So in general, if you talk about clustering the real data, then you can safely say that we are in high dimensions, and the clusters themselves are not filling up the space. They are sparsely located, and also very often the clusters would be in lower dimensional manifolds. So in three-dimensional space, one cluster would be a funny surface here, another one would be a curve there, another one would be an isolated little blob there, or some clusters might be actually three-dimensional. So dimensionality of the space and the dimensionality of the clusters, individual clusters, are not always the same. In fact, very often there are low-dimensional manifolds defining the cluster. The cluster points lie along low-dimensional manifolds. So you cannot just be looking for three-dimensional clusters in three-dimensional spaces. You should be also looking for two-dimensional and one-dimensional. What characterizes the cluster is also not very clear. In fact, it does depend upon the domain from which the clusters came, and you can't have general clustering algorithms if you are listening to every single domain's characteristics and using them into the clustering algorithm. Then you have to design one for each case. So if you want to have general clustering algorithms, then you have to have a general model of the cluster itself, and that's why this problem is difficult. Yes?
What's the embedding space? Is it the high-dimensional feature space, or is it the image space itself?
No, this one is high-dimensional feature space.
Feature space.
Yeah. So for example,
Like the low-dimensional manifolds embedded in this really
high-dimensional space, yeah, where the manifold points on the manifold come from. For example, they could come from subtrees. They could be our subtrees. Each subtree is captured by one point, or each region is captured, each node is captured by one point, and we are trying to find out whether there is a pattern to these recurring objects. Are they similar in some non-trivial way, which corresponds to lying along a smooth surface in a space? Who knows what space? We don't know. So the space discovery itself is a problem, because if you can discover manifolds, then you have also discovered what is it that makes them uniform. So the clustering, the literature on clustering is very old. People have been working on it for those reasons, from all disciplines, and introduce all kinds of algorithms. Now, this complexity is not that important here if you are going for GPU implementation or some exotic architecture-based computation, but it is useful in revealing some fundamental properties of the clustering clustering algorithms or clustering problem, you can see that the n is the number of points that are to be clustered in some space. You can see that there is a clustering algorithm that is linear. There is also a clustering algorithm that is horrible in terms of not practical. It is about 2.5, right? 2.5 or 4.5. There is also something that you can get in n log n. So the complexity here is referring to the computations performed on the points, but it also reveals something about the basic problem, and that revelation I think can be carried forward to the architecture at hand. If you know what your architecture can do, or your architecture that you want to design can be dictated by the properties that also result in these kinds of numbers. So I guess we don't have time for going into all of this. Here is an example of spectral clustering, where you have those clusters discovered by solving eigenvalue problem in a matrix that represents all the points, their relationships. Each point is compared with each other point distance-wise, how far it is from each pair of points, how far apart they are, and from that big matrix, n by n matrix, n being the number of points, you can then find these nice local blobs, or you can arrange them so that you find blobs. And how do you find blobs? You do further simple clustering. And so the summary of clustering, I would say, is that you need to n squared would be your minimum effort to do anything reasonable, and you can add to it, you can go away, you can reduce it, but the short answer is that there is no clustering algorithm today that you can say, okay, here is my point set, go ahead and give me clusters which are the same as a human being would find. If we can see 2 or 3 dimensions, we can find, but there is no clustering algorithm today in 2009 which can operate free of human intervention and do something reasonable. You have to be in the loop in order to do something reasonable. Back to the theme. So here is a data set that we collected ourselves here. The aim was to learn from this huge set, discover all the interesting things that happen, and find out the models, and then look for them in. So we had a training set. You find their occurrences in the data set, and here are results. So there we learned all different kinds of models that come, and here is what comes out from images that were not seen before. So you find out the occurrences of different objects that were learned, whichever occur. So now an important point. What we have done so far is that we have learnt these objects, and taxonomy rests on the fact that there is similarity among things. But there is also, if everything is similar, then how do we distinguish them? And the key point there is that every single category which looks like some other category also has something in it which distinguishes it from the other category. So if you were only to cover that part, chances are that you'll be more confused about which one it is. So here, for example, are the distinctive features that this thing discovered. All the models that it discovered, if you put them side by side, then these are the things where they differ. So for example, a deer has a signature feature, which is antler. A sheep has distinctive feature, which is this. And these are obtained by computing differences between their siblings in the same cluster at some level. Anyway, so what you can do is, without spending time on this, what you can do is you can take that thing into account, and when you are asked to recognize a mule, you won't worry about intermule differences. You will go to that level. But if you are asked to differentiate between mule and horse, then you will go to this space where you have emphasized those guys. So there is a conditional probability involved here. You put conditional probabilities where you say, how do I discover this category? You say, I should be looking for this. And if I find this, my conditional probability of discovering the parent category has become high. So you now embed those things into your calculations, and your quality improves. Anyway, so one more thing about something that would be useful to draw some lessons about computation, and that is that so far what we have had is pure hierarchy, and everything was a tree. But what we didn't have so far is that eyes, as long as eyes and nose and lips are there, we'll call it a face, as long as they have right properties themselves. Even if the lips are above and nose is below and eyes is to the bottom left and this eye is to the top right and all kinds of jumbled up versions of it, all of those will be called faces. There is no spatial layout. In fact, some people have that problem. Some people who have mental brain lesions do have this problem of not being able to recognize configurations, although they can recognize individual objects. So what we have,
You could put Picasso paintings and it would recognize this face?
oh, I see. You mean in terms of rearranged,
Because of the
distorted?
yeah, distorted eyes are square and this and
No, that is a geometric distortion.
it's a geometric.
Right. This one is topological distortion, where your layout has changed. And
It
this,
does both, I guess, layout and
right. So the other part has already been captured in the. If you saw enough Picasso, then it will build a Picasso model, because it will include that in the PDF, in the probability density function. But this one is a part of the structure. So what we have now is a tree, but a tree which is complemented with these links, which are neighbor links.
So if the picture is upside down, you can still.
Yes, 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 because it's invariant. The topology and geometry and color are invariant. If you relate it to the frame reference, then it's a different. This is not related to frame. This is also scale independent. It can be small or large. Anyway, so this is from the viewpoint of computation. It is important because what now we have come to is not tree matching but graph matching. Tree matching is much more friendly because you can traverse it in a friendly way, but here you have to go in all directions. Although it's not as bad as arbitrary graph, because it's a tree complemented with lateral connection, so it's sort of halfway there. It's 1.5 tree in some sense. So here now we have to deal with subgraph isomorphism. So I would say if our architecture can handle this kind of a thing, it'll go a long way in doing meaningful vision computations. If we can build this into the nature of the architecture, so that it is very hospitable to high-speed computation of these computations. And I'm not saying graph in general, but even this would go a very long way if it can configure itself dynamically to accommodate nodes, their links, both parent-child links and the lateral links. Okay, so let's do some quick. So that from what we had before to what we have now is a big difference. It improves a lot, the capability. So this same idea can be applied to a single image, not to many images. In the same image also you can discover many occurrences of the same object. So it can be used to find occurrences of the same thing across. So here you have a bunch of bees, and you can sort of discover the bees, each of the members of the family or the society individually. I don't know why it's not running. It was running before I came. Okay, so these are textures which are now these guys, where the bees are now suddenly moving and the fish are moving. So are there any computational issues which are different from what we have seen so far in these kinds of problems? So we came from static texture, now we're going to dynamic textures. So here the textures are a little bit more, little different from the bees and the slices in that these are fluid-like textures, these are particle textures, where there is no real element, solid element which is laid out or which is moving around. This one is, these are particles. So here the calculations that are involved, first of all the goal is to, so this thing basically the smoke is moving, and there is that similar motion, dynamic motion in the other cases. And the reason for doing this is that you can synthesize fire and smoke and recognize and compress it. And so this is the original sequence, and this is the sequence in the middle that we learned. And this is model based, and this one is some other model that is not as good. You always have to find something that doesn't work as good as yours. So, but in this case there are no examples other than more or less this is the only example, so we didn't have to look very far. The approach here is based upon Fourier domain. So there you have a different requirement on the computation. Now we are dealing with a computation that involves the whole array, but it's not just whole array, it's multiple, it's sort of n log n operation, because you have to divide it up into pieces and do the FFT, two-dimensional FFT. It's phase based, so the computation here would be that you compute the FFT, process FFT, and then invert it back. So that will be the dominant operation. So again, the FFT would be you can use it to recognize, the model can be used to recognize the textures with high confidence with those guys who are only half as good. You can use it to compress the textures. You can use the model to clean up the image, see through the window and there is snow, so you say, okay, I'm going to do my magic and remove the snow and make you see the building behind. Well, so there is your original, there is the separated smoke, and there is how the smoke looks, and now after removing it from the image you see the building behind. And this involves not only FFT but also standard numerical packages such as package for solving Navier-Stokes equations and convex optimization and all kinds of things like this. But those are all pixel operations. Those are not computationally anything more difficult than. So then what you can do is you can take your texture and put it against a different background, or you can give it a different color, put it in a, so there is your original and there is your the same texture put against a different background. All right. Computational issues are standard probabilistic analyses, but I think that the nuances here are not as much in architectural aspects, but in numerical and mathematical analysis aspects. Mostly small number of visits to each space-time pixel. Here is another example which probably won't. I don't know how many different computational aspects it will bring, but we have a system that we are developing which takes video of a passing train, and it discovers at the end the type of loads the train had. It's a freight train. It says, does it have truck containers, truck trailers, how many of them are there, what are the dimensions. The goal is for this statistics to be reported to the railroad management, so they can load the trains better, so that it saves fuel, which means a lot of money. So if it goes 3,000 miles across the country, and if you can the main thing is that it's aerodynamics that's coming in the picture. Because of aerodynamics, if you change the gaps between the loads, the fuel efficiency shoots up or shoots down. And so they don't know how to do it. So by collecting these statistics, they will discover what the magic is in obtaining fuel efficiency. So we do have actually a system that is installed outside Chicago in Joliet. And as the train comes, when it's about 200-300 yards, it triggers the system. The system starts to record. It's the weatherproof and so on. It feeds its information into the railroad system, their net, and it gets triggered. It records the data, and then it creates this long panorama of the train, which is from beginning to end. We collect about 5 videos per train, each containing 4,000 frames. So about 20,000 frames total, right? Yeah, on the per train. And our goal is to then discover what the loads were. The loads can be very funny. They can be big one above the small one, or small one above the big one, or one only, not two, or empty, nothing. You want to find out what the gaps were, where they ended, what the load was, which car was it on, because they want to find out who loaded it later on. So they want, and there is a automatic database, RFID system, which is tied to each of these cars, which sends you the signal. So the system here that we have, not our part, but the system captures that, knows which car it is, and relates the loading properties with the car. So you end up doing these kinds of labels which we have now. Or you can use, we have a cart that goes down the tracks and takes images of the track, finds out whether some things are loose, some things are missing at the track. Is the track going bad this way or that way? Are the joints good? Things like this. So those are the spike and anchor, and it just does some standard things that the Federal Railroad Association wants to make sure that they are okay. So computation-wise, basically the operations are neighborhood computations. What you do want to do is you relate frames. You want to relate frames with each other based upon these neighborhood properties. And in general, each point in the scene is visited as many times as you saw it as the train was going by from that fixed camera. So small number of times, 4, 5, 6 times. So the computation-wise, it's not that much of a challenge, except for the FFT, which we have already seen, which involves efficient computation. We also do that from underneath the train. We also have a system which sits beneath the tracks underneath, looks up both visually and thermally, and then discovers if the circuit is about to get hot, are the brakes failing because they're getting unnecessarily hot or unnecessarily cold because they're not applying, and things like this. So the train goes above it. It generates the same kind of panorama that we saw before from the side. The system now discovers problems and preventive maintenance related information. Another different kind of example that we have is if you have, instead of train, if you have a vehicle observing buildings or the train or any other object moving on the side, you want to create a 3-dimensional panorama of it, not just 2-dimensional panorama of it. And again, the computation here is space-time in the sense that you have successive frames and you correspond them just like we did it for panorama generation for the train. But computation-wise, you look at pixels here, neighborhoods in one, and you relate it to the next one. That's and the next one. So it's again on the order of n squared, not n squared. Each pixel and its neighborhood computed for some properties, and then you match them against successive frames. Finally, I did say acquisition. So I'll also tell you something about the acquisition-related parameters. Those are typically also array-based computations. Here we have one for our camera that we developed quite some time ago, which gives panoramic images, and the computations are, I'll summarize them. So basically 2 cameras. One is this kind where you have a long panoramic strip because the camera spins and gives you a panoramic strip as a result, which is omnifocused, where everything is in focus. And another one which gives you a hemispherical view. This is from view from the ceiling. It takes a hemispherical image with uniform resolution and a video. So the features here are that it gives you hemispherical view at uniform resolution with no pan tilt moving parts, but it does give you pan tilt without moving parts. So if you put it on the ceiling, for example, it will give you a view from in all directions without any moving parts, and you can record everything and come back to it. So computation-wise, like in any camera, when you start to use it, you have to make sure that the distortion is corrected, which is order n operation. You go to each pixel and you do something. That's not very challenging. Calibration is also same order. Display generation requires a lot of work. In fact, in our case, we use GPU because there is so much graphics computation that goes on that if you don't do it using GPU, there is no way you can do it in real time. So GPU is very, very handy here. In particular, for example, if you have the whole view and you want to construct specific windows from multiple different cameras, then you have to do the right matrix computations so that you have this perspective from this camera and this perspective from this camera fused together seamlessly. That involves simple computations, but matrix computations, and the GPU is just the right thing for it because it has OpenGL that you can use to do the computations quickly. So I hope that gives a variety of computations that not only are involved in our work, but also I think representative of the field of computer vision. Many years ago, when special purpose architectures were in vogue, Janak and some of our students, we worked on special architectures for vision in 80s, and then there were other groups doing these things, and it went on for 10-15 years. People built special systems both in universities and industries, but they all died because these general purpose architectures are so strong and they are developing so fast and they are so cheap that it doesn't make much sense to go the other way. And those were the result. The reason I brought this up is because those were directly the result of these such observations, that vision computations. The question was, what is it that you can do to expedite vision in general? And those kinds of computations I listed early, the local array, the global array, and so on, and object-based, which are not along a regular grid, or graph-based, those are critical. Being able to do those computations very fast is critical to do vision well in general. And I think we can do that today on general purpose architectures. All right, thanks. Any questions?
Okay, we have time for a few questions. And Naren, can you repeat the question so people watching?
Move the microphone. No, that's fine. You didn't mention anything about symbolic processing. That was one of the things I remember doing in the higher level of abstraction, right? None of these GPUs are good for symbolic processing. So what is there a lot of symbolic processing involved, or you just give up on symbolic processing?
No. So if you go to the upper levels of the tree or taxonomy, it becomes more and more symbolic. So the labels at the upper levels are more meaningful than down below. You start with pixels and you go to longish things, then you go to animals, and you start becoming more semantic. And the graph processing or tree processing involves explicitly symbolic processing, because what you have is symbols associated with these entities. They are linked with some other entities, so you have inter-symbol relationships, and the constraints, which we didn't go into, the processing involves inter-symbol constraints, which are nothing but those that correspond to the real world constraints. So if something can be above something or below something, then, for example, you won't call it a horse, a normal horse, if the legs are not below and vertical. The legs cannot be horizontal and the body cannot be horizontal. So they cannot be parallel. So those kinds of issues, and they are very much alive at the upper levels. So the higher level computation is symbolic, and those links, that the red links between neighbors, are associated with information like this. Yeah, John?
So I had a related question of what can't you do on the GPU, and it sounds like that was the answer to what you can't do on the GPU is graph isomorphism or the higher levels of.
Right. Because even if you do that, GPU is, you will be underutilizing it. You will be using it like any other machine. So really to make use of its massive power, you have to have a monolithic character to what you do. So I know there are people in the audience who are more GPU experts than I do, but I think we have done the front end stuff, the lens distortion correction, the display by using OpenGL. It's wonderful. But we have not tried more symbolic level, less regular computation on the GPUs. Yes, sir.
So Naren, in terms of the first part of your seminar, where you're doing the segmentation and classification, how far away from being real time is that process today? So assuming you knew everything about all the objects in the world, and you had the trees all built up, if you saw something new, how long would it take you to recognize
So I skipped the details for two reasons. One, for time, and second, to save myself some embarrassment. And because if we went into the segmentation alone, it'll take time. But that's not to say that we have tried hard to make it fast. Because you can, we all know that what looks like hours, if you think a little while, you discover, oh, wait a minute, I can reduce it suddenly to minutes. Because you discover this, not approximation. You can do things exactly, but different way. And so we have seen it enough, all of us have seen it enough that you know that you will find a good way. But of course, it's asymptotically not the answer. So the segmentation that we have done so far is not aimed at speed at all. But I think we can do it without any problem at maybe in maybe a small fraction of a second, maybe let's say 1 second, but that's not good enough. And so you need to go into these other things. So the question is, can we blend in with GPU in some smart way so that you can have the dual core or the triple core or quad core, whatever, doing general stuff, and then delegating it to the GPU as and when needed, kind of like a routine, right? And again, the question is, how do you smartly organize this so that there is scheduling is perfect? So all of those issues, but then they become sort of so specific to the thing you do that it's. So questions, are there general lessons for us to? That's where you guys come in. But yeah, the speed is an issue. Yeah. And another one, which gives you a hemispherical view. This is from view from the ceiling. It takes a hemispherical image with uniform resolution and a video. So the features here are that it gives you hemispherical view at uniform resolution with no pan tilt moving parts, but it does give you pan tilt without moving parts. So if you put it on the ceiling, for example, it will give you a view from in all directions without any moving parts, and you can record everything and come back to it. So computation-wise, like in any camera, when you start to use it, you have to make sure that the distortion is corrected, which is order n operation. You go to each pixel and you do something. That's not very challenging. Calibration is also same order. Display generation requires a lot of work. In fact, in our case, we use GPU because there is so much graphics computation that goes on that if you don't do it using GPU, there is no way you can do it in real time. So GPU is very, very handy here. In particular, for example, if you have the whole view and you want to construct specific windows from multiple different cameras, then you have to do the right matrix computations so that you have this perspective from this camera and this perspective from this camera fused together seamlessly. And that involves simple computations, but matrix computations, and the GPU is just the right thing for it because it has OpenGL that you can use to do the computations quickly. So I hope that gives a variety of computations that not only are involved in our work, but also I think representative of the field of computer vision. Many years ago, when special purpose architectures were in vogue, Janak and some of our students, we worked on special architectures for vision in 80s, and then there were other groups doing these things, and it went on for 10-15 years. People built special systems both in universities and industries, but they all died because these general purpose architectures are so strong and they are developing so fast and they are so cheap that it doesn't make much sense to go the other way. And those were the result. The reason I brought this up is because those were directly the result of these such observations, that vision computations. The question was, what is it that you can do to expedite vision in general? And those kinds of computations I listed early, the local array, the global array, and so on, and object-based, which are not along a regular grid, or graph-based, those are critical. Being able to do those computations very fast is critical to do vision well in general. And I think we can do that today on general purpose architectures. All right, thanks. Any questions?
Okay, we have time for a few questions. And Naren, can you repeat the question so people watching?
Move the microphone. No, that's fine. You didn't mention anything about symbolic processing. That was one of the things I remember doing in the higher level of abstraction, right? None of these GPUs are good for symbolic processing. So is there a lot of symbolic processing involved, or you just give up on symbolic processing?
No. So if you go to the upper levels of the tree, or taxonomy, it becomes more and more symbolic. So the labels at the upper levels are more meaningful than down below. You start with pixels and you go to longish things, then you go to animals, and you start becoming more semantic. And the graph processing or tree processing involves explicitly symbolic processing, because what you have is symbols associated with these entities. They are linked with some other entities, so you have inter-symbol relationships, and the constraints, which we didn't go into, the processing involves inter-symbol constraints, which are nothing but those that correspond to the real world constraints. So if something can be above something or below something, then, for example, you won't call it a horse, a normal horse, if the legs are not below and vertical. The legs cannot be horizontal and the body cannot be horizontal. So they cannot be parallel. So those kinds of issues, and they are very much alive at the upper levels. So the higher level computation is symbolic, and those links, the red links between neighbors, are associated with information like this. Yeah, John?
So I had a related question of what can't you do on the GPU, and it sounds like that was the answer to what you can't do on the GPU is graph isomorphism or the higher levels of.
Right. Because even if you do that, GPU you will be underutilizing it. You will be using it like any other machine. So really to make use of its massive power, you have to have a monolithic character to what you do. So I know there are people in the audience who are more GPU experts than I do, but I think we have done the front end stuff, the lens distortion correction, the display by using OpenGL. It's wonderful. But we have not tried more symbolic level, less regular computation on the GPUs. Yes, sir.
So Naren, in terms of the first part of your seminar, where you're doing the segmentation and classification, how far away from being real-time is that process today? So assuming you knew everything about all the objects in the world, and you had the trees all built up, if you saw something new, how long would it take you to recognize
So I skipped the details for two reasons. One, for time, and second, to save myself some embarrassment. And because if we went into the segmentation alone, it will take time. But that's not to say that we have tried hard to make it fast, because you can, I mean, we all know that what looks like hours, if you think a little while, you discover, oh, wait a minute, I can reduce it suddenly to minutes, because you discover this, not approximation. You can do things exactly, but different way. And so, we have seen it enough, all of us have seen it enough that you know that you will find a good way. But of course, it's asymptotically not the answer. So the segmentation that we have done so far is not aimed at speed at all. But I think we can do it without any problem at maybe in maybe a small fraction of a second, maybe let's say 1 second, but that's not good enough. And so you need to go into these other things. So the question is, can we blend in with GPU in some smart way so that you can have the dual core or the triple core or quad core, whatever, doing general stuff, and then delegating it to the GPU as and when needed, kind of like a routine, right? And again, the question is, how do you smartly organize this so that there is scheduling is perfect? So all of those issues, but then they become sort of so specific to the thing you do that it's. So question is, are there general lessons for it for us to? I mean, that's where you guys come in. But yeah, the speed is an issue. Yeah.
So how far away is the current technique from the objective of answering such a question? For example, I asked, if Tom Cruise is in this movie, then can this be answered with current?
So that's Deming's question also. Whether it's a human face, that's one question. Whether it's Tom Cruise versus Tom Cruise with beard or Tom Cruise's brother who looks like him.
So
if you can tell the sister apart, that's good enough.
So the current technique is able to tell that this may be his family, right? Maybe Tom Cruise's family is
Yeah.
so actually.
So I think the answer is this. Are you dealing with a friendly Tom Cruise or adversary Tom Cruise? In other words, is Tom Cruise willing to be recognized? If so, then Tom Cruise will not move and stand in front of you and do everything to help you. But if Tom Cruise is walking through this in a suspense movie where the lighting is all dark and everything, then it's very difficult to.
You can say, it's 90% Tom Cruise, right? Something like that.
Depending upon how dark it is. So I think the other issue is that what I discussed here was category recognition, which is to say, are we dealing with, let's say, Caucasian humans? Tom Cruise is one of them, right? Men, Caucasian. So can we do this category level recognition? Because then we are deliberately downplaying the differences that occur within the category, and we are looking for the differences across the category, and we are counting on those. And those things are many times at loggerheads. They are opposite. So if you do one thing, then you lose the other many times. Therefore, it's good to go to category first. So now that you have narrowed it down, now you start pulling out the fine differences, hair-splitting differences, and now you start telling differences between Tom Cruise and others. But then some other issues come. You have to normalize, and with respect to lighting and so on. So I would say today's technology in unrestricted settings for face recognition is not yet there. Face discrimination specifically. So discrimination under known conditions is okay, but if you want to recognize under general conditions and you want to do the subtle things, we are not there at all.
What's the role of the tree? It seems like once you add things horizontally, I guess I'm not quite sure why you have what you're using that original tree structure for.
That's the famous. We use the famous British paradigm: divide and conquer. You just take the image, you split it into pieces, and you have smaller objects. So that means that now you have your computation is limited to smaller number of pixels and more relevant pixels. So one is purely the computational advantage. Second, yeah.
But you're still matching on all of them, and you're doing clustering.
Yes,
as well,
yeah.
right?
Here is the reason why this thing works. I mean, world is made up of objects, right? Objects are made up of cohesive matter. So, for example, when I look at 90% of the objects, or most of the objects, are spatially localized. Why? Because nature doesn't build things which are related but are far away. It's a very basic design principle. So anything of interest that you think of, most of the times it is localized spatially, because it is an entity. An entity has relationships among its parts, and parts cannot be related over long distances. I mean, something like that. This is a very lame reason, but it has meaning. So objects are localized. So when you have an image of a scene, the transformation that takes place from scene to image is perspective transformation. Perspective transformation does not change. For example, lines remain lines, disks become elliptical, but they don't change seriously. You don't fragment them. So as a result, in the images, meaningful things in the world are still meaningful are localized in the image. And therefore, if you do a jigsaw puzzle based decomposition, which is in some sense generic, and I'll tell you what, so then you will get this kind of a recursive thing because parts are inside the objects. Now, the other thing is what we are doing is decomposing based upon photometric properties, because in the beginning we have no idea what the objects are. It turns out that in real world, if two things are nearby and unrelated, chances are they will not be the same color, unless nature has built a green insect on a green leaf to camouflage, right? So except for those cases, you have in general independent things are independent, so they don't have the same color. So there is always a boundary. So when you look at the image and you look for color discontinuities, very often it means semantic discontinuities. It doesn't have to be different object at this level. It could be different object this level or that level or that level. So it's a very good indicator on the way to finding objects from while bootstrapping your way out of complete ignorance. You don't know anything. So you just put your hands on these discontinuities and hold on to them. It turns out that eventually they are very likely to map onto something meaningful later. So our tree captures discontinuities of those kinds in the hope that we are not dealing with a green insect on a green leaf camouflaging itself, but it's just a friendly natural condition, in which case meaningfully different objects will show up as these discontinuities. And you don't commit to them, you just do it. And then trees are bigger than they should be, but they are hopefully not losing out anything that you would need later. So that's why trees are good to have, it seems. And they don't require any commitment. You're doing it based upon very basic principles. So once you build a tree, you have gotten rid of a lot of junk, because number of nodes in the tree is very small compared to pixels. But they are good platforms for you to then hang coats of horses and mules and high-level descriptions.
Thank you, Narayan. It's been a very enjoyable talk.